Thank you for coming, and thank you for staying this long through this this long process. But our project is intelligent parking. We're going to go through a team introduction of who we are for you that don't know. We're going to go into the problem that we wanted to face, the requirements that came from that problem, the solution that we derived using those requirements, and the schedule and budget we plan to use to build our project, as well as the progress we've already made. So I'm Sean Potter. I'm a project manager. I'm a computer engineering major, and I did most of the database research.
Hello, I'm Nick Tanasso. I'm an electrical engineer. I'm the hardware lead for this project, and my research so far has been around sensors.
My name is Michael Yaboot. I'm an electrical engineer, and I did the research on wireless communication.
My name is Michael Mattis. I'm a computer engineer, and my focus was on the web application.
I'm Yulin Yi. I'm an electrical engineering, and I'm doing the power research.
Okay, so you might have guessed by now that the problem we're looking to tackle is parking. We've all been frustrated with parking before, trying to find a spot, whether it be on your way to work, if you're going shopping, trying to find a spot on the street. And this is becoming ever more frustrating with the number of cars on the road increasing, as you can see in this graph. The current estimate in the United States alone for registered cars is around 260 million.
And with this problem being so vast, with so many different ways it could be tackled, we decided to take just the contained setting of garage parking to start with, because if we can solve that solution, our solution can be adapted and scaled for more complex like street parking. So here's the three different things that are out there today. So valet is one of the most common that's used to solve this issue, but it's very costly because you have to pay people to actually park your cars. The second is like visual cues. So inside parking garages, they have like arrows to point you which directions to park, but they have to be built into the garage. And third is this newer technology, the smart parking. This is embedding it's a sensor, but you have to actually build it into wherever you're trying to put your parking spots. The problem with this is there's a lot of bad reviews on its accuracy, so we try to tackle this sensor detection with also succeeding with the accuracy results.
What you see here is our objective tree that breaks down our marketing and engineering requirements into 4 major categories. We have accuracy, where we need to make sure that the data being recorded to our database is correct and only proper information is what's given to the user. We also want to make sure that this is an easy system to maintain. It'll be something simple to install. You don't need to pay someone to click in for you. You don't need to hire a specialist to deal with it. It's also going to be durable. Since this is a parking garage and obviously accidents happen, we don't want, say, a car runs over it and it's gone forever. Parking garages are also exposed to the elements, so whether it's rain, snow, hot, cold, the device shouldn't have issues with it. It'll also be powered for years, so we want to make sure that. It'll also be safe, since obviously since we're dealing with drivers, we don't want people to be distracted while looking for parking. So the user interface will be very simple.
Okay, so with all those objectives in mind, this is a quick sketch of our proposed solution. We want to design a parking block that is smart enough to know when the spot is taken. It will also be smart enough to communicate to its neighboring blocks, which will then communicate to a controller, which will then talk to a database, and in the end will communicate that information to the user through a smartphone application. We're going to go over a little bit more detail on each one of these modules.
In the parking block section, it's driven by a microcontrollers called ATmega328 PPU Arduino system. We picked this microcontroller because it has the lowest power consumption of all our research. And this microcontroller is controlling the IR emitter, sending an encoded IR signal to detect whether the car is there or not, and reflect it back to our IR sensor. And our whole block is powered by a solar panel with a small battery installed in it in case of the solar panel doesn't work sometimes. And I think it lasts as long as at least 5 years. And the whole system tracks 1 to 4 minutes. to reduce the total power consumption of the block.
When this 1 to 4 minute check occurs, we want this data to get to the database. Before we get to the database, however, we need to get to our controller. We're going to do this by using a Zigbee network, a Zigbee-based network. Zigbee allows for us to use a mesh-based network so that each individual parking block can relay its information to the controller. The controller that we've chosen to use is a Raspberry Pi 3 Model B. The reason we chose this controller is because it's Wi-Fi and Ethernet compatible. So the parking lot owner can choose whichever to his convenience. We also chose this because it's easy access to the database.
So once we have this information in the controller, we want to process this information and send it to the database. Now, we don't want to send information to the database that's already there, so we're going to process the information and only update what's changed. So if a new car is coming into the lot, we're to only send that data to the database. We're using Amazon Web Services to host our database because they allowed us to have a free 1-year subscription, so that'll fulfill the requirement we need for our Capstone project. We're using MySQL as our primary database, but we also have an instance of SQL Server just in case we run into problems. We have a second one that we could use. We're also looking to follow the third normal form, which is for databases, so we don't have redundant information, which could also cause errors if we're trying to update tables and we're not supposed to. Some of this information needs to be encrypted, like if you're the lot owner or your security personnel having different access to these applications, we want to make sure that we have this information stored so if our database is breached, we don't lose any important information. And finally, for ease of access for developing these applications and also for security purposes, we have stored procedures that are also going to be implemented in our database.
What you see here is our application broken down into 2 major categories. User application, which will be on a mobile device such as Android or iOS, and then the lot owner application, which will be desktop. The user application will allow them to view, select the lot, find spots, select floors. It'll just allow them to see what's available to them. The lot owner application, however, will allow them to have full control over how they want to change their lot. Maybe they want to set restrictions, notifications, maybe they want to shut down a certain floor for maintenance. They will be able to do errors. It'll give them complete control over what they want to do.
So this is just a visual representation of what Mike just went over. This is a use case diagram, and it demonstrates 4 most common use cases. And so on our right, we have the driver and the passenger. We don't want to create distractions for drivers. We want to have like minimal to 0 distractions. So we want to implement a voice control recognition system, and that's the only difference between the passenger and the driver when it goes through the processes of finding an empty spot. On the left, you'll have your owner and the security. They'll both need to log in because we need to make sure that only people with the right permissions are allowed to change what they need to.
So for our risk analysis, we had 2 criteria when we were breaking down our risks that we currently have. The one is the most likely to occur, and that's how the rank is calculated. The second is severity, and that's if this does occur, how bad this will be for our system. Actually, the reason why the first one's on the list is because that actually occurred for us last week. We found out that Bluetooth was not going to be efficient enough to transfer this data through the parking lot to the controller. So we switched out to Zigbee, and we're in the beginning phases of Zigbee. So the second is the solar panel could possibly be inefficient. Since we are inside, we do know that we can power solar panels using fluorescent light, and it might not be efficient enough to power our system entirely. So we're looking to add a battery with that, or just completely replace it with a battery if it's cost effective. The 2 medium severity ones, those are easier just swap out replacements if something does occur. So if we find out that the IR is not accurate enough due to either interference or just the outdoor environment, we will switch to ultrasonic or a combination of both. And that's just taking the signal and processing it differently. The environmental durability, we will be testing our block through all the different phases, like through water, through people running it over, all this different thing. But we might not contain all the possible outcomes that could occur with actual real environment. So our plan would be to either redesign the physical layout once we find a problem that has occurred and why it occurred, or give out a 1-year warranty so that you could have it tested through all 4 seasons. The 2 low-risk problems that we have here, is whether a hardware, a software, or a project leader is not available due to some case that we cannot control, we have sort of a depth chart that somebody will step up and take over those roles, depending on which tasks are being completed by which person. But we think that's going to be very low severity because we all know that we're good workers, we could pick up for each other if there's a problem. The last is, this is actually a discussion that we were talking about. Since our system is modular, there's a potential that somebody might just pick up the block and steal it. We don't know what the demand for these blocks are, so we have a proposed route to go through if this is taken, and that is to have additional security fasteners sent with this device, to have some sort of installation that you could do to protect from people actually taking your devices if that's a big problem for some establishments. So this is very complicated. I just want to break it down into 4 main groups. This is our schedule that we've been working on since October. The green is the parking block, what we've been working on in the parking block. Blue is controller, red is what we've been working on with the database, and yellow is applications. Since we've had a few changes, we're a little behind on the controller and the parking block, but with the database and applications, we're moving ahead. So we'll be able to take those resources and put them into catching up with the parking block and controller. The pink on the bottom represents the actual tests that we're going to do when we combine these systems together. We actually just connected our database to our application, so we have a working demo with that. We did, and this blacked out on the bottom is our semester milestone. And we did everything that's prior to this we were supposed to meet, and as I mentioned, we just changed our Bluetooth to Zigbee, so that slowed us down with how we're going to use the communication between the blocks. But we think that we've made we've hit our 40% because we've hit more of our software than we expected. So it ended up balancing our system. Our estimated budget for this project, this is the entire budget that we propose that we're going to need to use. This includes 5 infrared. It's one 5-pack that'll get you for $6. A Raspberry Pi, 1 Raspberry Pi, 3 microcontrollers, because we want to make sure that we can make this system work with multiple different devices. We don't want to just make one device and say, oh, it works. We got to make sure the mesh network works. 2 battery packs, because this is since we haven't gone through our power consumption yet, because we don't know exactly what we're going to use, whether it's going to be just IR or IR and ultrasound, we wanted to just limit that we have 2 different possibilities for our battery packs. We have, just in case we have run into an issue. We have 1 solar panel. That'll be our final decision, and that's the estimated value that we'll need to use, because I was looking them up, and this is the range that we're looking for, the size that we're trying to put onto this block. We're going to have 3 Zigbee modules that for the three different blocks, and then 1 parking block. So this is the 6-foot parking block that they put in front of cars. We want to put our system on one of those to show it that it works as a functional system. And our subtotal comes out to $240, but for an individual block, it would be around $100 to $120. And that's just with making one, like a small production. So if you have more devices you want to produce, the price